Let's delve into the pigeonhole principle. This principle states a fundamental concept. If you have more pigeons than you have holes, then at least one hole must contain more than one pigeon. As an example, consider the scenario where you have 10 pigeons but only 9 pigeonholes. According to the pigeonhole principle, at least one of these 9 holes must contain 2 or more pigeons. Here is the formal definition. If n items are put into m containers with n greater than m, then at least one container must contain more than one item. Using mathematical notation, we can represent this as the ceiling of n divided by m is greater than or equal to 2, when n is greater than m. In this notation, n represents the number of items, which are the pigeons, m represents the number of containers, which are the holes, and the ceiling symbols indicate the ceiling function, which rounds a number up to the nearest integer. Consider this simple example, the birthday problem. Imagine there are 8 people in a room. Given that there are only 7 days in a week, at least 2 people must share a birthday on the same day of the week. For instance, Monday may have 1 person, Tuesday may have 2 people, Wednesday, Thursday, Friday, Saturday, and Sunday each have 1 person. In conclusion, at least one day must have 2 or more people born on it. Here is a real-world application of the principle in computer science. Hash table collisions. Imagine that we have a hash function. This function takes a key and returns a bucket number. For example, our hash function is defined as key mod 10. So we have 15 items in 10 buckets. The keys are 11, 21, 31, 12, 22, and so on. The buckets are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Since 15 is greater than 10, at least one bucket must contain multiple items, resulting in a collision. Here is an application of the principle in network theory. This is the Facebook friendship paradox. In any group of 6 or more people, either 3 people all know each other, or 3 people are all strangers to each other. This is a direct application of the pigeonhole principle in social network analysis. Let us consider the application of the principle in cryptography. This is the birthday attack. Consider a hash function where you are trying to find a collision. This means that you want to find 2 different inputs, input A and input B, that produce the same hash value h of x. With 2 to the power of n divided by 2 attempts, you can expect a collision in an n-bit hash function. This is a much smaller number of attempts than needed for a brute force attack, making it a significant concern in cryptographic security. Let's see an application of the principle in data analysis, especially in data sampling. Imagine that you need to detect duplicates in a data set. Let's use a code example using Python. We have 1,000 samples and 365 possible days in a year. We define a function check duplicates that takes samples and bins as input. If the number of samples is greater than the number of bins, then the function returns true, guaranteeing duplicates. This means that in any dataset with more records than categories, duplicates are mathematically guaranteed to exist. Here are the key takeaways from this discussion on the pigeonhole principle. First, it is simple yet powerful. It is a basic counting principle, but it has profound implications across various fields. Second, it has universal applications in computer science, cryptography, data analysis, and network theory. In conclusion, the pigeonhole principle proves that impossibilities become certainties when resources are limited. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.